All right, so now let's focus on equilibrium. And so equilibrium is going to be a very big topic, and especially some of the topics within this topic are basically one of those guarantees for the exam. Now, we first have to talk about what equilibrium is, some factors about equilibrium, and then some kind of changes in equilibrium. But first, let's talk about what equilibrium is. And so to do that, we need to talk about reversible and irreversible reactions. Now, I should also say real fast, part of this explanation I'm going to give for equilibrium is going to be explained in an interesting way. And that interesting way is going to be through using another chapter we've already talked about, rates and rate laws. But so if you're okay with that, or if you're okay with equilibrium in general, stick around. But if you're not, I would definitely go back and just relearn what rates are and what rate laws are. So here we have the introduction. And so this first reaction we're going to be considering is the explosion of TNT. And so when TNT explodes, it turns into 12 carbon dioxides, 5 hydrogen gas, 3 nitrogen gas, and 2 equivalents of solid carbon. Now, as you can probably imagine, TNT, after it explodes, doesn't really turn back into TNT. This reaction really goes one way. It reacts, and then it doesn't return into TNT. So here is the reverse reaction. These molecules coming together to form TNT. This reaction does not happen. You really won't see this, and because of it, the reaction of TNT turning into those 4 different reactants, or those 4 products, is considered an irreversible reaction. Now that you know what an irreversible reaction is, let's look at what happens when N2O4 gas turns into 2 equivalents of NO2. You're probably a little bit less familiar with this reaction, but when N2O4 gas turns into NO2 gas, it's not going to stay that way. For every one that turns back, let's say if 100 turn back, some of those NO2 molecules can react and reform N2O4. So molecules of NO2 that are formed from N2O4 are not destined to always remain NO2 molecules. So the forward reaction can happen, N2O4 turning into NO2, but also the reverse reaction can happen, which is those NO2 molecules coming back together to reform N2O4. And so, as a result, this reaction does not go one way or to completion. It is a reversible reaction. Now, reversible reactions that don't go to completion have some kind of equilibrium. So what do we mean? Well, there's some point that the rate of NO2 turning into N2O4 is the same rate that N2O4 turns back into NO2. And so that point that they are both equally turning as fast from N2O4 into NO2 is called the equilibrium point. Now, if you're totally good with this, let's keep going. All right, so how we're going to learn about equilibrium here and why the amounts of reactants and products do not change, and then as well, why the forward rate and the reverse rate are equivalent, is through an example using rate laws and rates. So if you haven't actually covered rate laws and rates yet, go back and look at the kinetic section. So the way that this is going to work is we are going to start with the concentration, rate law, and rate for a given reaction. And this reaction is going to be the one that we previously talked about for a second, which is the reversible reaction of two equivalents of NO2 reacting to form N2O4. And so what we're going to do is we're just going to say, hey, we have a solution of pure NO2, and we're going to see what happens as NO2 starts to react to form N2O4. And if we're talking about equivalent rates, we are going to be looking at the rate laws and see how they change. So the rate law for NO2 is just rate equals the constant K times NO2 squared. And then the rate law for N2O4 is rate equals K times N2O4. And that's basically it. We're also going to say that there is a set rate constant, right? Rate constants are for a single reaction and depend on the temperature, but not the concentration. So one reaction, let's say for this reaction, that rate constant is going to depend solely on the temperature, but not how much NO2 is there. So the rate constant does not change, and that rate constant will be completely separate from the rate constant for N2O4. So, like we said, we start off with some amount of NO2, and that amount is going to be 2 moles. So, what's going to happen? Well, we're going to input this in as the concentration of NO2, and we're going to also introduce what our rate constant K is here. So these values in red are completely made up. Don't worry about what they mean, just worry about the concentrations. Now, the concentrations for the rate that N2O4 turns into NO2 is currently 0 because we don't have any N2O4 yet. For NO2, it is 2 just because our starting concentration is 2. Now, while the rate is going to change, that change in rate is due strictly from the change in concentration, not the rate constant. So, what is the rate right now for both of these reactions? The rate for the reaction of N2O4 is going to be 0. We don't have any N2O4, so it's going to be kind of hard for it to react. And the rate for NO2 is 0.676. So if I had to plot this data, I would say, well, if this is the rate, and we are saying that it's going to equilibrate at some point, this will just be the reaction progress. Sorry, I should have done this a second ago. And so what's going to happen is right now, this rate is very high, while this rate is basically 0. So which one of these two reactions is going to have the fast rate? Well, NO2 is the only one that has a rate right now. So we will say that this blue line here, this blue line is the rate of N2O4. So right now we have a pretty high rate, and that is 0.676. And then on the flip side, we have the rate of, this is the rate of NO2. And down here we have the rate of N2O4. And that is going to be 0 right now. So at the start, we have these two rates. Great. Now, as this reaction goes on, what's going to happen? Well, more and more of this NO2 is going to react, which means we're going to have a lower concentration of NO2, which means this number is going to get smaller, and it's going to also affect our rate. Now, on the flip side, as our NO2 reacts, it forms N2O4. And so this concentration will go up, and we'll start having a positive rate. So now let's look at what happens in the middle of this reaction. When we've already had our initial, we're now halfway through the reaction progress towards equilibrium. We are going to have the concentration, rate law, and rate again. And let's say halfway through, we find that we have an N2O4 concentration of 0.07 and an NO2 concentration of 1.86. Now, you might be saying to yourself, well, I have these two concentrations of these different molecules, but that doesn't add up to 2. Well, it doesn't, but you just have to remember that one N2O4 is made from 2 equivalents of NO2. So if I really multiply that by 2, I have 0.14 times 1.86. I would have my 2 moles again. So now what are the rate laws? Well, my rate laws aren't going to, my rate constants are not going to change, but my concentration is. So now N2O4 has a concentration of 0.07 moles per liter, and NO2 has 1.86. So what's going to happen? Well, I'm going to have an increased rate for N2O4, at least more so than I did initially, and that's now equal to 0.25 if you do the calculation. What's going to happen to the initial rate of 0.676? It's now going to go down because we just lost some of the NO2 molecules, so our concentration is lower. So the new rate is 0.585. And if you look here, I still have the exact same rate constants. They are just experimentally determined, nothing to worry about. Just keep focusing on the concentrations and the rates. Now, let's say this reaction is now getting to an equilibrium. So the final concentration, actually, before I do this, let's just go and plot this. So now, what is my rate of NO2? It's 0.585. So let's say we're right around here now. 0.585 is my rate for NO2. And at the same time, my rate for N2O4 is now 0.25. So I'm now actually registering a rate for N2O4. How are we doing on time? Doing all right. Cool. So now what happens? Well, I find that my final concentration is 0.14 moles for N2O4 and 1.72 or 0.14 moles per liter for N2O4 and 1.72 moles per liter for NO2. We look at our rate laws again. Fantastic, no change in our values for the rate constants. And the final rates are equal to each other. Now that's interesting. This is our equilibrium point. The rate that N2O4 right here is turning into NO2, 0.5, is the same rate that NO2 is turning into N2O4. But what else is strange about this? Well, and this is probably one of the most confusing things to students, my concentrations are not the same. My concentration for N2O4 is roughly a 14th, the concentration of NO2. Fascinating. So, what does that mean? Well, first, let's just say the rate here. At equilibrium, my rate for one reaction is equal to the rate of the second reaction, and that's an equilibrium. Now, this graph is going to be slightly different. Let's just do this real fast. So here is my, let's say we're still talking about blue, right? So this is NO2. And this down here is going to be N2O4. And this is concentration. So as the reaction went on, I started with a concentration of 2, and I ended at 1.72. So here's my start, and then let's say right here is my end. So I would look like a better version of this. So at some points that, I'm not going to stand for that. At some point we leveled out. You know what? Let's just take that. What the? Fascinating. Anyway. Same thing is going to happen for my N2O4. That concentration is going to level out, no. And it's going to not change anymore, because as my N2O4 turns into NO2, my NO2 is turning back into N2O4. So I have equal concentrations because the rate of transformation from one to the other is proportional. So there's the initial, and then I find out that my final, let me do this, 0, and then my final was 0.14. And so that's what's happening. That's why at equilibrium, rates do not change. They are now equal to each other. And the concentration of both reactants is now the same as well. So join us as we go into the equilibrium constant.